SpaceX had two rocket aborts in the same week, Starship and Falcon 9 back-to-back, for two completely different reasons. Then Starship flew anyway, 33 Raptor engines, 18 million pounds of thrust, and for the first time ever, the ship came home completely intact. The Pentagon's missile tracking satellite network just hit the halfway mark. 63 satellites now in orbit, closing in on a fully connected battlefield network. All of that, plus a double star hiding in the Big Dipper, a buck moon washing out this month's meteor showers, and what's worth staying up for. This is This Week in Deep Space Digest. After two delays, one engine swap, one tropical storm, Starship Flight 13 finally launched on July 24th, and it delivered one of the most important test flights in the program's history. Quick recap of how we got here. The original July 16th attempt aborted at the last second when several Raptor engines failed to ignite. SpaceX replaced 6 engines on the booster and updated hardware and software. A second attempt was then delayed another 24 hours by cloud cover from Tropical Storm Bertha. Third time was the charm. This time, all 33 methane-fueled Raptor engines on the Super Heavy booster fired flawlessly, generating 18 million pounds of thrust. About 2 minutes into the flight, the vehicle executed a clean hot staging separation, and the upper stage continued on towards space while the booster began its return sequence. The booster completed its boost-back burn using 13 engines and executed its flip maneuver successfully. But the recovery failed during the final landing burn over the Gulf of Mexico. Of the 13 engines required to restart for the landing burn, only 10 came back online. By the moment of splashdown, only 5 engines were still running. Without enough thrust to slow down properly, the booster hit the water hard and exploded on impact. It's a real setback for the booster side of the program, but it's worth remembering the booster had already done its job by that point. It delivered ship to where it needed to be. The landing burn failure is a specific, isolatable problem for engineers to chase down, not a fundamental flaw in the vehicle. While the booster struggled, the ship itself had arguably its best flight yet. Powered by its 6 Raptor engines, it continued on its suborbital trajectory and successfully reignited a single Raptor engine in the vacuum of space. This is the single capability the entire Artemis moon program has been waiting on. Relighting an engine in the vacuum of space with propellant that's been sitting in tanks during coast is mandatory for any mission that needs in-orbit refueling, which is exactly what NASA's lunar Starship architecture requires. One analyst noted there may still be minor issues to iron out in the relight process, but the core capability is now proven. This flight also carried something no previous Starship test has carried, a genuine operational payload. 20 next-generation Starlink V3 satellites, each capable of delivering roughly 1 terabit per second of downlink capacity. The satellites deployed at an altitude of about 124 miles through a side dispenser mechanism. SpaceX engineers have compared it to a giant PE's dispenser. During a brief 20-minute operational window, the satellites extended their solar arrays, established laser links with older Starlink satellites already in orbit, and communicated successfully with ground stations. Because Flight 13 flew a suborbital trajectory on purpose, the satellites weren't meant to stay up. They burned up on re-entry about 20 minutes after deployment, their job already done. Surviving hypersonic re-entry is what SpaceX has called Starship's biggest remaining problem for full reusability. To gather better data this flight, 6 of the deployed Starlink satellites carried cameras aimed back at the ship to monitor its heat shield in real time. Engineers even painted several black thermal tiles white to simulate damage and test whether the remote cameras could actually spot structural vulnerabilities from orbit. The ship survived re-entry wrapped in super-hot plasma while beaming back live high-resolution video the entire way down. After surviving re-entry, the ship executed its belly flop maneuver, flipping from horizontal to vertical by sequentially firing 3 engines, then 2, then 1. 1 hour and 5 minutes after launch, it achieved what SpaceX called its softest splashdown ever, landing in the Indian Ocean northwest of Australia. And for the first time in the program's history, the vehicle stayed completely intact. It didn't explode on tipping over. It floated belly up in the water, giving SpaceX's recovery drone the chance to inspect it up close before it was lost. On the morning of July 20th, SpaceX's Falcon 9 rocket attempted to launch 24 Starlink satellites from Vandenberg Space Force Base in California. At exactly T0, all 9 Merlin engines ignited, and then, less than a second later, they shut down. SpaceX posted a brief statement on X, standing down from today's Starlink launch. Vehicle and payload remain safe. And that was it. No explanation, no timeline for the next attempt. The Falcon 9 had already completed 84 successful launches in 2026 before this abort. It is statistically the most reliable large orbital rocket ever built. The last time a Falcon 9 experienced a post-ignition pad abort was June 14, 2024, more than 2 years ago. In the entire history of the program, it has happened a handful of times. Understanding what happened requires knowing how a Falcon 9 ignition sequence works, because a pad abort is not a malfunction. It is the safety architecture doing exactly what it was designed to do. The ignition sequence begins at T-2 seconds when a highly reactive fluid called TATB is introduced into the engines. It ignites spontaneously on contact with oxygen, spinning the turbopumps up to 36,000 RPM and generating 10,000 horsepower per engine. During this 3-second window, the rocket is physically held to the pad by clamps, while the flight computer analyzes hundreds of real-time parameters: turbopump behavior, chamber pressure, fire intensity, valve positions. If any reading falls outside expected margins, the computer triggers an abort a half-second before the clamps release. That half-second is the only practical window to safely stop a failing rocket. Once the clamps disengage and the vehicle lifts off, an engine anomaly near the ground would result in a catastrophic loss of the vehicle. The system caught something it didn't like and stopped the rocket. That's not a failure. That's the detection architecture performing flawlessly. The booster on this mission, designated B1082, had already successfully flown 22 times, including high-stakes national security missions for the Space Force and the NRO. At 22 flights, it's firmly in its prime reuse window. Refurbishing it costs roughly $300,000. Building a new one costs $30 million. SpaceX has every reason to be patient, do this properly, and not rush it back to the pad. The Falcon 9 abort came just 4 days after Starship Flight 13 aborted at Starbase in Texas, when 4 Raptor engines failed to ignite. 2 SpaceX vehicles. 2 aborts. 1 week. The obvious question is whether they're connected. While SpaceX was dealing with aborts on 2 fronts, a different Falcon 9 mission earlier in the week had gone completely according to plan, and it was arguably the most strategically significant launch of the week. On July 16th, a Falcon 9 lifted off from Vandenberg carrying 21 military satellites for the Pentagon's Space Development Agency. The mission, designated T1TLE, brought the SDA's Transport Layer constellation to 63 satellites in orbit, exactly halfway to its planned 126 satellite size. The Transport Layer is the communications backbone of what the Pentagon calls the Proliferated Warfighter Space Architecture, a network of small satellites in low Earth orbit designed to provide resilient, low-latency connectivity for military operations globally. Missile warning, missile tracking, battlefield data relay, all of it moving through this network. The key technology is optical intersatellite links, laser beams connecting satellites directly to each other at nearly the speed of light, without routing data through ground stations. This cuts the delay that conventional satellite communication suffers from and makes the network much harder to disrupt. You can't take down a distributed mesh of 126 small satellites the same way you could target a single large military communications satellite. Before we wrap up, 3 things worth going outside for this week. Tonight, if you have binoculars, point them at the Big Dipper. The middle star in the handle, Mizar, actually splits into 2 separate stars, Mizar and Alcor, once you look closely. It's one of the most famous double stars in the sky and was reportedly used by some ancient cultures as a natural eyesight test. Easy binocular target, no special timing required. July 29th brings the full buck moon, named for the time of year male deer begin regrowing their antlers. Look for it rising large and golden on the eastern horizon that evening. So, to recap the week, SpaceX had 2 rocket aborts for 2 completely unrelated reasons. The Pentagon's missile tracking constellation hit the halfway mark with its laser mesh still dark, and Starship Flight 13 finally flew, losing the booster on landing, but nailing the in-space engine relight, deploying real Starlink satellites for the first time, and bringing the ship home intact for the first time ever. We'll be back next week. You know what to do. See you then.